Hi, welcome to this video. I'll be going through a question from the Cambridge University Press International A-Level. The subject is chemistry, and I'll be going through an A-Level question. An A-Level question that was originally printed and published in November 2020. Now, hopefully you'll be able to see the screen. You can see the annotations that I'm doing on the screen as well. I'll take you through it as you would probably need to be taken through it if you are practicing for a test on equilibrium chemistry. Equilibrium chemistry is really, really tricky. It's a really tricky topic for many students. And if it's not the theory, it's actually the time management. So I'm just leaving the QR code. You can scan the QR code and you can get a copy of the actual paper. It's printed on lots of websites on the internet. I've chosen Physics Maths Tutor. So you can find a copy for yourself if the screen is a little bit too hard to see or if you want to see how the rest of the paper was. It was November 2020, and on that website you can also find the mark schemes, but I'll be going through the answers in real time within this video. Okay, so this actual question was a really nice question in terms of tackling the topic. It wasn't picking on a particular part of equilibrium. It's equilibrium chemistry always seems to be like question 3, question 4. Sometimes, and I've seen some more recent papers where paper 4 where you actually have um, equilibrium embedded right in the middle of an organic question towards the end. It's sometimes it can be really hard to unpick, but this particular question was a really nice question, I feel, and one that I've picked out because it actually encompasses a lot of what you need to learn about further aspects of equilibria, all within one question. So it gives you it gives you a good idea. If you feel as though you've revised it, it gives you a good idea as to how well you can actually do this. So it starts off, and I'm just going to quickly go through the actual question itself. It starts off with some mathematical expressions that you need to be able to recall, and then there's a calculation of pH given some data, and then there is a Ka question. You have to work out the pH from that using the relationship that you have memorized. It's pretty important for you to memorize the relationships before you go into the exam as well. And then it skips forward to partition coefficient. So there's a partition coefficient question, and then you have to do a calculation as well, probably based on separating funnel scenario. Okay, right. So we'll go into the question straight away. Okay, so the question starts off with some of the work that Friedrich Oswald developed in his lifetime, around about the beginning of the 20th century. Give the mathematical expression for each of the terms pH and Kw. So pH, I'm hoping that students can definitely memorize this term. pH is equal to minus log to base 10. Now, in chemistry, you may not necessarily have to put the 10 according to exam schemes. I always like to do it because I just like to be a little bit thorough. And you have to multiply that with the concentration of H plus that is within your solution. So that's the answer to that one. It's a very, very clear expression. Now there's an alternative way of giving that. I'll just pop that here. If you wanted to, some of the mathematic aficionados may prefer to have that as Lg. Concentration. It's really important that you put the square brackets as well. Because in chemistry, square brackets actually does mean concentration, the concentration of the substance that you have. Okay. And Kw. So Kw is the next one. Kw is the ionic product of water. So that is something that you will have to come up with. It's all to do with the fact that the extension of ionization of water is very low, and you can still think of it as being in an equilibrium, but the concentration of water is pretty constant, and we can therefore incorporate this into the value of Kc. So it would be the concentration of H plus multiplied by the concentration of OH minus. Okay. And that value is called the ionic product of water, and at 298 K, that is equal to 1.00 times 10 to the minus 14. And you notice that there are two concentration values, so the units will be mole squared decimeters to the minus 6. In water, you can actually use that equation to find the hydrogen ion concentration in pure water. For each molecule of water that ionizes, one H plus ion and one OH minus ion are produced. So the concentrations in pure water would actually be equal. And so Kw would be concentration of H plus squared. If you rearrange that, you can then work out the square root of Kw as being equal to 1.00 times 10 to the minus 7 moles per decimeters cubed. So that's how it's useful. Okay, so those questions should be pretty straightforward because it's standard recall. And then we're going to move on to the next part of the question. And the next part of the question asks the candidates calculate the pH of 0.027 moles per decimeters cubed of NaOH. Now, what you've got to do is you've got to look at the question in part A, part 1, and you've got to try and think how much of that is perhaps useful for me to know and put into place for part 2. So do I need that? The answer is yes, you do. You do actually need both parts. So we would know from Kw that Kw is equal to the concentration of H plus, concentration of OH minus, and that is equal to 1.00 times 10 to the minus 14. Okay, that we know. And the concentration of the sodium hydroxide within the question is 0.027. So from that statement, we would know that when this dissociates, and sodium hydroxide is a strong alkali, it's a strong base, so it will dissociate. The actual concentration of the OH minus would also be equal to 0.027 because it's a strong base. So it seems to be the case that we actually already now have this value here from the question. That's that. Okay. And so if we then incorporate that times 0.027 is equal to 1.00 times 10 to the minus 14. If we then divide both sides by 0.027, there we go. The 0.027s cancel out on this side here, and we're just left with this term, which is the concentration of H+. So the concentration of H+ would actually be equal to 1.00 times 10 to the minus 14 divided by 0.027. Now, at this stage, it is very, very useful for you to think and do a quick check within the question. How many significant figures do I need to use in my answer? Because you're going to come out with an answer here. So justifiably, you've actually got 2 decimal places, you've got 3 decimal places, and you've also got 2 significant figures. So what do we do? Well, in this particular question, when you do the calculation, this works out to be 3.7037 times 10 to the minus 13. Okay. So it would be too harsh for us to round this up to 4 right in the middle of our calculation. I would also argue that because it's such, because we're working with quite small numbers here, the 3.7 over here on the right hand side is also it's also too early to round up this number to 3.7. So I would leave that number as it is. If you actually put it in the calculator, I'll give you a chance. You have a chance now to put it in the calculator. I'm going to put it in the calculator at the moment. If you actually put it into a calculator, I would put the brackets around the 1.00 times 10 to the minus 14. If you divide that by 0.027, you actually get even more. You get 3.703, and then it's 4 because there's a recurring number. So after the 7, there's actually a 0. You wouldn't need to go anywhere beyond that. But my advice is keep that value in the memory of your calculator, or don't do another calculation within your calculator. So you actually retain that number in there. The question is now asking. The question goes back to asking what the pH is. So we've worked out what the value of the concentration of the hydrogen ions are, and this is where we go back to the first question. We've actually utilized this, and now what we need to do is we need to figure out what the pH is. So we need to utilize this as a very good example of why it is that the recall of these equations is so important. Because if you weren't able to come up with the actual equations themselves, you would actually be dropping not just 2 marks at the beginning, but a 3rd mark with the calculation. There's no way in which you can do the calculation without coming up with the equations itself. So it's like you're being punished twice. But you're also being rewarded twice if you come up with it. So the part 2 of question A is an application. So now what we're going to do is we're now going to move on to working out the pH. Okay, so the pH would be equal to minus log to base 10 of your value of H plus and that would be minus, just need a little bit of space here, minus log 3.7037 times 10 to the minus 13. And that value actually comes up as 12.4 when you use 3 significant places. Now I'm going to put this into my calculator. I've got my calculator off the computer. So remember, I didn't press any of the calculation buttons. The 3.7037037 times 10 to the minus 13 is still in the calculator. So I'm going to press the minus button, and then I'm going to press log, and it opens up the brackets, and I'm going to type in answer, close brackets, and it comes up as 12.43136376. So I'm just going to put that value underneath just to give us an opportunity to think about rounding up and down. 376. Okay, so that value is now coming out. So the 3 won't round up the 4 over here. And looking back over the question, so you have 2 sig figs, but you have 3 decimal places here. And then you have in your kW value arguably 1 times 10 to the minus 14. So you're in a situation where you've got to try and think, right, okay, what if I used two significant figures in my answer? If I use 2 significant figures in my answer, my pH would be 12. But very clearly, the pH is not near 12 completely. It's 12 and a bit. And when we talk about when we talk about concentrations of H plus, it's quite a big significant difference. So having a feel of this is useful. And the mark scheme actually says that you need to have a minimum of 3 significant figures. So how do you actually get around this? Well, what you could do is you could actually put in your value of the calculator. So in this situation, it would probably be a good thing if you had the time to put in the full value of your calculator's reading into the pH. Now that would be a fail-safe method of securing the single mark. You do all of that calculation and you don't want to lose that mark right at the very end, especially when they say 12.4 has to have a minimum of 3 significant figures. If you can't do that, then and if you don't choose to do that, then what you will have to do is you'll have to remember that when you go into your examination, you will have to give, if you get pH questions, you'll have to give a minimum of 3 significant figures for it. Okay, so that's where Cambridge actually expect candidates to be able to come up with the right level of significant figures, which may sound a little bit unfair, but that's just the way that they assess. Okay, so we're going to move on to part B now. So part B is now talking about Ka value of chloric 1 acid, HClO, which is 3.72 times 10 to the minus 8 moles per decimeters cubed. And the question then asks, calculate the pH of 0.01 molars HClO, so moles per decimeters cubed. Now, what can you lift from the question itself so far? Well, the first thing that you probably want to do is you probably want to write down an expression for Ka. Now, the expression for Ka would then be something along the lines of, if you wanted to just do a little bit of a jot here. So your Ka would equal concentration of H plus. I'm going to leave the state symbols out because this is just working out, just for the sake of brevity. ClO minus concentration of HClO So that would actually be uh, the equilibrium constant for this acid. And if you isolate the H plus, that would actually so that would actually be the expression that we would need to progress with the calculation. So let's have a look now as to what information we have and whether we can actually simplify this expression. Well, it's very, very clear that when you have an acid and it dissociates in this form, because this is a monoprotic acid, because this has only got one H coming off over here, then you have a situation where the concentration of this H plus would actually be the same as the concentration of the A minus, because the HA has to dissociate, and for every H plus you have an A minus. So in this situation over here, for every H plus you'll have a ClO minus. So these two can be collapsed. We can just take that away and simplify it. And that actually makes things a little bit easier. The second thing that we can do is we can read the question and we can find out from the question that the concentration of the HClO here is given as 0.01. So this will now become 0.01. 0. And we've also been given the Ka value. And the interesting thing about this question is that they don't tell you anything about the strength of the acid. They actually want you to determine that from this number. Now you notice that this number is very, very small. It's 10 to the minus 8. Because it's 10 to the minus 8, that means that the denominator of this expression is much larger than the numerator. And that means that the HClO stays intact. This is actually a weak acid. So because it is a weak acid, we can therefore assume that very little dissociation takes place, and that's how we can assume that the concentration is close to 0.01 for these types of calculations. So we're going to go ahead now with our isolation of H plus. So this Ka value here has been given as 3.72 times 10 to the minus 8. And now if we multiply both sides by 0.010, these two terms cancel out. Okay, that becomes 1. So now we've got a situation where you have the square of H plus being equal to this numerical term, which is really, really useful. What we can now do is we can square root this term. To get the concentration. And I think you now know how to do the rest of this, because once we have the H plus, we can work out the pH from the expression that we picked up in A part 1. This makes this a really good question. So let's square root this. So pop that in your calculator. And when you put it in your calculator, I strongly advise and encourage you to put brackets around everything, really. You could actually bracket this until you do like a double bracket. So I'm putting in my calculator, square root, it actually comes up with the bracket, so you can put another bracket in 0.010 multiplied by open bracket 3.72 times 10x minus 8, close bracket, because you have two brackets, and you then come up with 1.9287305152 times 10 to the minus 5. Okay. So I'm just going to shorten that to 1.9287 times 10 to the minus 5. Okay. And then what you have to do is you have to process your pH calculation. Eight seven times 10 to the minus 5. Now this isn't already stored in my calculator, so I can just click the minus, log, answer, close bracket, equals, and that then becomes 4.7147. Okay, 4.7147. And just to be consistent with the one above, I'm going to one five. Okay, you can summarize that as 4.72. The mark scheme actually asks for two significant figures in this particular example. So that first decimal point is, again, something when you practice your questions, pay attention to the mark schemes. They actually tell you exactly how they want it expressed. So 4.7 is absolutely fine in this situation. Okay, so it's an inconsistency with the mark scheme. 3 sig fig for the top one. It's only because it's in double figures. It's 12 point something. And the one below is in single figures, 4 point something. So don't forget to give that something. Okay. All right. Okay. So now I'm going to move on, and the question does move on. So I'm just going to scroll back over here. So it's really, really important. Please, 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 please make sure that you memorize this equation over here. Okay. Minus log to base 10. This term, this definition. All right. And in the question itself, it says give the mathematical expression. Okay, for each of the terms. So you must make sure that you go in, because without those mathematical terms, you can't do the rest of the question. It's like you have to memorize these mathematical terms anyway. And it's like they're giving you these terms to, first of all, frame up the actual approach to the question, to get your mind geared up to thinking about the rest of part A and then part B. And the second thing that they want to do is they want to reward you for the effort that you've done, you've put in learning those two expressions. And without those two expressions, you suddenly lose 4 marks out of 7, which is significant, because more than 4 marks is roughly, 4 out of 7 is 57%. And if you've done that already within this question itself, the paper 4s start to reward you with a C grade standard once you get to 52 to 54%. So if you've done all of these correctly, you've not dropped a single mark, you're already up to the C grade, and now you're then opening yourself up to potentially the B grade and the A grade. Okay. All right. Okay. So now what we can do is we're going to look at part C. Water and octan 1-ol form two layers when mixed. Ethanamide is more soluble in water than it is in octan 1-ol. Okay, ethanamide. It's more soluble in the water than it is in octan 1-ol. When 1 gram of ethanamide is added to 50 grams, 50.0 centimeters cubed of water, it just happens to be 50 grams anyway, and this is then shaken with 50 centimeters cubed of octan 1-ol. It is found that the water layer contains 0.935. That's a lot of information. Okay, so why not do a quick sketch of what is going on? So when you're in your exam, just try and figure out. Now, this is a separating funnel. Your teachers should have shown you a separating funnel, but if not, just quickly Google one. There's some very, very pretty pictures of it. Just do a quick sketch. So ethanamide. So there's two layers that form. Okay, so let's have the top layer. Okay, water and octan 1-ol. I'm going to take a guess. I'm going to say that octan 1-ol is something that floats on water. So I'm going to say that this is the water layer. Whether it floats on water or not is not really relevant within the question itself. So water and octan 1-ol. There's your two layers. So this is your octan 1-ol. This is your H2O. This is your water. Ethanamide is more soluble. When 1 gram is added to 50 centimeters cubed, so this is 50 centimeters cubed. Obviously, 50 plus 50 is equal to 100. And you start off with 1 gram, and then you shake it. And that means you'll need a bung here. It's found that the water layer contains 0.935. Now, immediately, if you started off with 1 gram, this would therefore contain 1.00, take away 0.935 grams. Okay, and that's the ethanamide. Okay, and that's at equilibrium. Okay, so the equilibrium that's taking place is over here. Okay, at the interface. Calculate the partition coefficient for ethanamide in water and octan 1-ol. Now, the partition coefficient gives a couple of statements, and it involves concentration. So when you talk about partition coefficient, you might be tempted to start to go into into a kind of like a movement where you start thinking about concentrations. You have to start converting things into concentrations. But there are actually a couple of tricks that you can deploy, and these tricks are very, very important for you to 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 understand, because this can then save you time within your exam. So this is a 1-mark question, and 1-mark questions are that they they can make or break candidates. This is why this is such a really important aspect to this question. Cambridge know that they're giving it 1 mark for this, and they know that students are going to look at this and they're going to think this is so much work to dig that 1 mark out. Is it worth it or not? Immediately, it's a really good what we call a differentiator between students that are grade C and students that are grade B, particularly when you have students who are pressed for time. So I'll do the full calculation, and then I'll show you a couple of tricks that you can deploy in order to save yourself time. And once you know those tricks, you can actually use that trick to tackle this type of question in the future. So the expression that you want for the KPC is you need to first of all understand that the ethanamide started off in water. Okay, so because the ethanamide started off in water, if this was like a situation where you had reactants going to products, you would actually put your reactants underneath as a denominator when we talk about when one's talking about equilibrium equations. So because it starts off in water, you actually put the concentration of the ethanamide in water at the top. Okay. Now that may be counterintuitive, but you can actually get 2 possible coefficients depending on whether you actually have solvent, the solvent at the top being water or the solvent at the top being octan 1-ol. So there is obviously a situation here where you could actually come up with the wrong one. So in this situation, it's really important for you to read the question and see what the order is in the question itself. Which one is mentioned first and which solvent is mentioned second? So coming back to the actual partition coefficient, so you kind of think if this was, so to reiterate the point I've just made, you might think that you started off with water and that would be your reactant. So you might be forgiven for thinking that the denominator is the concentration of the ethanamide in water. But the way that the question is written is very important, because when they say calculate the partition coefficient for ethanamide in water, which is where it was at the start, and at octanol, whereas where the ethanamide is moving into, so that's your product. If you want to think about this as being like in terms of reactants and products, it's not obviously a chemical reaction, like as per se changing. It's just changing the solvent. So argument for another day. But you might think that the reactants, the reactant side, the water goes at the bottom and the product is at the top, but that's not actually the case. The way that you should think about it is the way that it's dictated in the question itself. So really important for you to read the question. Okay. So when they give you the question and they say in water and in octan 1-ol, they want you to put the concentration in water at the top and octan 1-ol at the bottom. Okay. Now, if you were to proceed with the question, you would think, right, concentrations are expressed in moles per decimeters cubed. And so you'd have like an expression with moles per decimeters cubed here and a moles per decimeters cubed here. Okay. Now, because you've got ethanamide, you might think, right, okay, ethanamide, what I need to do is I need to now work out the number of moles. So the number of moles equals mass over molar mass, and I need to work this out, and I need to work this out because I've been given the mass. So there's a function here. There's to convert it from mass to moles, you have to divide it by mR. Okay, so you might be tempted to go down that route. If you did that, then somewhere along the line you would have a division by mR here. And you'd also have to do a division by mR down here. Okay? So that would convert it from grams to moles. The other thing that you would also have is you might be thinking, right, I've got a figure in centimeters cubed. So I've always learned in GCSE that I divide it by 1,000 to convert it to decimeters cubed. Okay? Now, what do you notice about what it is that you're doing to the top number and what you're doing to the bottom number? Now, if you worked out what the molar mass of ethanamide was, let's say it was X, just for the sake of argument, you'll notice that the numerator and denominator have this statement of X, which means that when you're doing your calculation, this would cancel out. And furthermore, the conversion of centimeters cubed to decimeters cubed requires the same division by 1,000. And that cancels out as well. So remember what we did in order to figure out what the moles were. We divided it by the mR. And when we talk about it, we're talking about the number of grams. And to figure out decimeters cubed, we are starting off with centimeters cubed. So the shortcut to take, which saves you a massive amount of time, and is the main reason why this is a 1-mark question, is that you do not need to work with anything other than the grams that they have stated. And all you need to then remember is which one's at the top and which one's at the bottom. So 0.935 remained in water, and 0.065 remained in the octane 1-ol. 0.065, I should say, moved across, and 0.935 plus 0.065 is equal to 1 gram. Okay, so that's your little self-check. Okay, so there's a nice little check that you can do at that stage. And the volumes, you've got to remember at this stage, do not combine the volumes because they are immiscible layers. Okay, they are layers that do not mix. The principle of partition of a solute between two solvents and the use of partition coefficients is within two immiscible solvents. And immiscible solvents are solvents that do not dissolve in each other, so they form two separate layers. So you can't combine the volumes. So the volumes are given in the question. As 50. It would be like 0.935 grams per 50 centimeters cubed. If you wanted to express that as whatever moles, you just divide that grams by molar mass of ethanamide, and then you would divide the 50 by 1,000, right? And we've been through that. So the ratios, the proportions are actually exactly the same, because the MRs and the thousands cancel out. So this is the calculation that you need to take forward. And again, all you need to do then is you just need to remember that water is at the top. You read the question itself and you see that water is given in the question first. Even though you might be thinking, oh, right, okay, start off with the reactants and go into products. So if you start off with reactants, then you have to have water as a denominator, but it doesn't work that way. Okay, so put that in your calculator. In actual fact, the smarties amongst you will also realize that the 50s cancel out, which makes this a very pretty question. So the answer is simply 0.935 divided by 0.065. And the answer comes out as 14.38461538. Which is obviously a mouthful to write. KPC does not have any units because the units effectively cancel out. We went through that here. Grams per centimeters cubed cancels out, and that cancels out. So it's just a ratio. And for this particular question, I would certainly not penalize 2 decimal places here, but for the question, the Cambridge accept a minimum of 3 significant figures for this one. You could actually get the marks just from 14.38, or even put in the full calculator. Okay, now the final part of this question talks about what to do with this water. Okay, so the 50.0 centimeters cubed of water containing this 0.935 grams of ethanamide is then shaken with 100 centimeters cubed of pure octane 1-ol under the same conditions. So this is where the 50s will not cancel out. Okay, you've now worked out what your KPC value is. So this is going to be used in this question here. Now you will get some credit for error carried forward if you made an error. We're going to assume that we did not make an error here. So your 14.38461538, which is your KPC value, is then equal to your number of grams per centimeters cubed. So you can take the shortcuts, but don't just divide grams by grams. Is my advice. Now, you know that something is going to move across. You know that mass. You don't know what that mass is. That's the unknown. So let it be x. Let it be x grams. Okay. If you're not comfortable with x, then just say mass. Okay. It's just 4 letters. All right. X grams is fine. So you know that you're going to have, and to be consistent with what we had before with the water and the octanol, you know that you're going to have an expression like this. So you start off with 0.935 minus a mass, okay, let's say that's x, and that is going to be divided at some stage with, so this is the mass at the top, and the mass that goes into the octanol is your x. Now what you need to do is you need to incorporate the fact that the volumes are different. So you start off with 0.935 minus x, which remains in 50 centimeters cubed, and the x that goes across is now dissolved in 100 centimeters cubed. which if you really wanted to, you could cross that out, and that becomes a 1, that becomes a 2, if you really wanted to. But you could put it through your calculator. So that then becomes 0.935 minus x over half x. Okay. If you multiply both sides by your half x, (14.38) over 2, which is your half, x equals 0.935 minus x. So we're almost there. What you need to do is you need to get all of your x's on one side. So if we now add x to both sides, 14.38 divided by 2, x plus x equals 0.935. Therefore, so now I'm going to put that in my calculator. So this looks as if it's at a stage where I can put it through. So 14.3. In actual fact, I had the answer still stored in the calculator for 14.3846. So if I divide that by 2, I get 7.19. If I add x, so that's 7.19 x plus x equals 0.935. So 7.19 x plus x is 8.19 x. So therefore, 8.19 x equals 0.935. Therefore, and if I divide both sides by 8.19, I should get x, because that cancels out. X equals, so I've got the answer 8.19 in my calculator. 0.935 divided by answer gives me 0.11413, 1455. So my final answer, just going to make it very clear in the box, 0.114 grams. And the grams is given already. Minimums 2 significant figures. Error carried forward, but there are no errors with this one. And that's it. So I hope this walkthrough has helped you, and I'd love to make a few more walkthroughs as well, but I need to know your comments. And the whole point of this walkthrough is primarily to help my year 13s who just need a little bit of aid and support, but heck, why not share the expertise and do it for free, because chemistry should be something that's loved by everyone. So a couple of take-home points just to summarize. Make sure that you learn your mathematical expressions by heart when you go into your exam, because they will help you. Make sure that you use the right level of significant figures for your values of pH and KPC. And finally, when you're doing your KPC, read the question very, very carefully, because it might go against what you think in terms of instinct for equilibrium. when they give two solutions in the question, make sure that the first one goes as the numerator and the second one goes as the denominator. And lastly, if you are having to put in too much work for a particular mark, there's probably a better way. So talk to your teachers, discuss it with your friends, and try and see whether there's a shortcut that you can take. I wanted to say shortcake. I think it's time for a break for me, so it's a good time for me to log off. I appreciate a like, and if you subscribe, you will know when I do some new ones. So take care. I really hope that was useful. Thanks for watching. Bye.